now it's time to say the first big thank to you, David. And here's our speaker today, David Widmann, PhD student in Sweden at the Uppsala University. And he's working there also with Turing, as also with other packages, with Julia packages, but yeah, he has also a couple of commits he made to the Turing.jl package and yeah, some other packages here and there. He will going to tell you how the whole ecosystem works and more. Thank you, David, for giving the talk today, giving us an introduction to Turing.jl. And with this, I would give the stage to you. Thank you so much for coming.
Yeah, thanks a lot for this nice introduction. Let me see, I'll try to share my screen. Can you see my screen?
I can see. This remembers me of one thing. And so we are going to record this session. And so feel free to raise your voice and be active in the Julia community. But if on the other side, you don't want to be kind of seen on the recording, of course, you can turn off your video or the like. Yeah, just for the tech enthusiast, so we are using Jitsi here. They are streaming to YouTube, where we have now a private stream, and this is how it works, and it works very well. But yeah, so we are going to record the session. Again, back to you, David. Thanks.
Yeah, okay, thanks again. I hope you can see my screen. I wasn't sure before.
Yes.
Okay, and yeah, it's nice to be here. Now I'm slightly embarrassed to see that so many people that are already familiar with Turing are here also today. So we'll see how well my talk and what I've prepared fits into this group. So I wasn't sure how familiar people are with Turing already. And actually, also the title, I should say from the start, it's not only about Turing.jl, but also about all the different packages around it. And I mean, maybe first a bit about me. I'm a PhD student at Uppsala University, as you already heard. I have a background and connection to Munich, actually. So it's nice that I was invited to give the talk today. I'm working in the field somewhere in between statistics, machine learning, mathematics, probability theory. My topic of my PhD is uncertainty of very deep learning, so that's a very broad field. And for my master thesis, I worked a lot with packages from the SciML ecosystem and contributed to the delay differential equation solver in particular. So I guess also the selection of the examples today is a bit biased due to this history of mine. And then I started to contribute to the Turing ecosystem at some point. And actually, that's not really kind of the focus of my PhD. So it's more of a fun side thing. And one connection is that a former colleague at my division in Uppsala, he is still developing a Birch. So maybe some of you are familiar with probabilistic programming languages, know that. And so that's kind of was the first time I was introduced to a probabilistic programming language. I guess nowadays almost everyone has seen these SIR models. So I thought that's a kind of nice start, and also fits into my topic of differential equations. It's used to model infectious diseases like influenza, and nowadays also, I mean, you can model COVID, but I guess basically most models that are actually used are more complicated than this very basic model that you can see here. So the main idea is you have three different compartments. You have a group of susceptibles, a group of infectious people, and a group of recovered, or sometimes it's called removed people, because it's also includes the ones who die. And So then the transition from one group to another, that's modeled by differential equations. And in this very classic, basic setting, it's these equations that you can see here. And so there are some parameters here. One is this beta, that's the infection rate, and then you have the recovery rate, that's the gamma. And then, susceptibles are S, infectious I, and recovered R. And one usually assumes that the total population is constant. And so when you work with ordinary DPQ, the SciML ecosystem, then you can see here how you could implement this in Julia, this model. So you have state U, and it consists of the S, I, and R of the different compartments, and then you model and compute the different differential equations and write that to the DU. And here's just some example configuration. So when we start with almost all people being susceptible and only 10 infected in this scenario with these parameters, then this is what you would expect over time, if we assume that, of course, everything develops according to the model. And then of course you can get the different behavior. Now let's see if this works. It's always a bit dangerous to do this live demonstrations. It seems there's some lack, or I'm not sure, maybe not really working. But you get different different behavior, of course. And so this model is then, you want to use this model to make actually predictions or reason about, should you make any interventions? Should you isolate specific groups? Should you like now with COVID, put restrictions on the whole society, some lockdown? But the problem is usually you don't know the transmission rate. You don't know the recovery rate. You usually don't even know the initial number of infected individuals. And so you might just know, for example, the population size or the initial number of recovered people, which is just set to 0, or like newly infected individuals for some days. But then also this might not correspond to the actual true numbers. So it's how to deal with all these kinds of uncertainties. And the idea of probabilistic modeling is then to not only have these fixed parameters, but to actually model the uncertainty of these unknown parameters with probability distributions. And I try to illustrate this in this plot here, so we can see there's parameter beta. And I mean, it could be very spread out, like the green curve, or it could be very, very densely centered around a specific value, like in the blue curve. And this, of course, makes a difference when you then make predictions, because in one case you're quite uncertain about the true value of the infection rate beta, and then the other case, it seems you have more knowledge about the correct values. And so the Bayesian approach is then to basically learn these probability distributions from the data. And this is kind of the general thing that you want to get at. Beta is what I used to denote all the parameters. So like beta, gamma, maybe the initial number of infected people. And Y's, these are our observations. So for example, number of newly infected individuals on a sequence of days. And now, of course, one could write down some model for this probability distribution kind of out of the blue. But since we want to learn this from the data, we make use of so-called Bayes theorem. And that just tells us that there is this relationship between the conditional distribution that we're interested in, the probability of the theta, the parameters given our observation, and the probability of the observations for a specific set of parameters, our initial assumptions about the parameters, and this denominator, which often is the problem, as I will come to in a moment. So usually what you do then is you formulate a model for the so-called likelihood. That's this probability of the observations given your parameter. So like in the SIR model, we are then use a model that tells us how do the daily cases of newly infected people, how do these depend on the parameters beta, gamma, and the initial number of infected individuals. And that's one component that we have to know is maybe a bit too much, but that we have to decide on. And then the second thing that we need to set is the prior, it's called. So that should incorporate ideally our initial beliefs and knowledge about the parameters. So for example, in this scenario, we know the infection rate can't be negative. So it would be a bit strange if we would say that it could be like -10 with some non-zero probability. And similarly, for example, one could assume that the number of infected individuals should be a natural number. And when we have set these two components, then basically, in an ideal world, we could compute the conditional probability that we're interested in. So we could learn what's the distribution of the parameters given our data. But as I said, the problem is really usually the denominator, because you can reformulate that as an integral over this product of likelihood and prior, as you can see here. But it's often not possible to compute this analytically. And to make this, what I said now, a bit more concrete, I go to the very classic example of flipping a coin. So assume we have a coin with unknown probability of heads coming up. And then we flip the coin n times. And k times we observe head. And the other times it's tail. And so now what we want to infer is the unknown probability of head showing up. And so this is a simpler setting than with the SIR model as before, and that's why I chose it now to illustrate these basic concepts. So our model then could be the observations, so the number of heads coming up is distributed according to a binomial distribution. So we assume every coin flip, they are all independent, and then with probability p, we get a heads on. We repeat that n times, so that gives us a binomial distribution. And and then this is just how it looks for a certain configuration of parameters, the binomial distribution. And now it works again. And you can see, depending on the value of p, it might be more focused towards our value of n, which is 10 in this simple scenario here. It's likely to show up more head, or in the other way, basically almost no, in none of the experiments we will see heads showing up. And then one very convenient choice in this specific example for a prior distribution is the beta distribution. And I'll come to this in a second, why this is very convenient. So the beta distribution that might seem a bit intimidating, maybe, but actually when we choose alpha and beta equal to 1 as parameters, then we just get a uniform distribution. And that's what's shown here. So when we choose these two hyperparameters, then basically it's like our initial belief is we don't know, every probability would be equally likely. And then of course if we assume that the coin is quite biased towards tails, for example, then we could think this is a more reasonable initial guess. And so yeah, the exact choice of the prior is really it's a design choice. And then this specific choice is very convenient because actually here is one of the few examples where we can compute the so-called posterior, this conditional probability. And it's just another beta distribution, but with slightly modified parameter values which depend on our observations. And there's a special name for this scenario, for these families where the posterior is of the same form as the prior and as the conjugate priors. But of course, this depends on the fact that we actually have a binomial distribution as a model. So only this combination of the prior and the likelihood gives us this specific property. And now we can make some example here. So for example, if the coin is a pair coin, so the true probability is 0.5, and we flip the coin 50 times, then we can we simulate a number k here of observations of hats showing up, and this, as you can see, it's really just some random choice, and I didn't fix it to a specific value, but I let the computer sample it for us. And then if we use a uniform prior, so with alpha and beta equal to 1, then our posterior that we would derive, our distribution of the parameter would actually be this very symmetric and centered probability distribution of P. And now this is, of course, also because the number of coin flips was just, the number of hats showing up was just 25. But also interesting is to observe what happens, for example, if the true probability is not 0.5, so if it's not a pair coin. And then we see that, for example, of course, we already observe a lot fewer number of hats, so 12 now in this case. And then also the probability distribution that will be shifted more towards smaller values. Let's compare it. So it was 22% I chose as the true value, and in this specific experiment, I ended up with a distribution which is whose mean is around 25%. Okay. And as I said, often it's not possible to compute this posterior distribution. So there's just saw in the chat there's a question. Is the vertical a probability, and if yes, why does it go to where are the values above 1? And the reason is that so in all this presentation, also the Bayes theorem, I don't really distinguish between a discrete and continuous probability distribution. I just use the small p for all of them. And in the case of continuous distribution, like the beta distribution here, where it's a range of values that you can observe or sample, then it's the probability density function, which is denoted with the p. So it's just kind of the shaded area below the curve that has to integrate up to 1, but the values, the individual values of the probability density function, that can be above 1. So that's the reason here. Okay, as I said, it's often not possible to compute the posterior exactly. So then the idea is for many methods, and what I will talk about today is basically instead of deriving this distribution analytically, we just approximate it as a weighted mixture of point measures. You want to put it mathematically. So that means we use samples and try to approximate the distribution. And this then allows us to also, for example, approximate the expected value of the parameter with these samples, or more generally, any function of the parameter, which can be very useful when you want to make predictions afterwards and use the infection rate to compute something. And so here's an example. This is Bimodal Distribution, it's called, because you can see these two peaks. And this is the actual distribution on the left, you can see there. And now on the right, you can see an approximation, which is based on 500 samples in this case. And of course, if there's fewer numbers of samples, like just one sample, then it's probably not a good approximation. But if we increase the number of samples, then you can see how we got can approximate the distribution better and better. And at some points it's just everything is blue and it looks very similar to the left hand side. And now another question is, how do we get such an approximation? And there are different methods, like, for example, importance sampling, which I don't want to talk. I won't talk about today. Sequential Monte Carlo methods, which I also won't mention in the talk, because slightly different concepts, and I thought it would be easier to leave them out. And there's the so-called Markov chain Monte Carlo methods, which we will use in the rest of the talk. And the main idea now, coming a bit more towards the topic of the talk today to Turing, is that there are a lot of different Markov chain Monte Carlo methods. So all of them give you a sequence of samples, and that will hopefully then, I mean, it's theoretically guaranteed, they will approximate this posterior distribution. But there are a lot of different ones, and in the Turing ecosystem, they then live in different packages, so that you can use them independently of each other. Because for some problems, specific methods are better suited, and some have special assumptions, like this elliptical slice sampling approach you see listed here, that requires normal distributions as prior distributions. So you can't use all of them interchangeably. And another point is that actually you can use these packages, and you can compute these approximations of the posterior distribution even without using the Turing.jl package. And many concepts actually, and the many things, how to run the analysis, how to perform inference, and so on, are standardized and similar across this different range of packages. And that's mainly due to the abstract MCMC package that you can see at the top of this list. And this package defines the general interface for a Markov chain Monte Carlo algorithms. And so then the user-facing API for many of these packages is very similar. And it's easy kind of to replace them in the Julia code, even though, as I said, you might not be able to do that depending on your model, or if the methods have specific assumptions. And then also kind of another odd fish in this list of packages is MC chains, because it's not for sampling the chain and for obtaining the samples, but for analyzing and visualizing them. And additionally, the Turing package itself, it also supports other packages that are not part of the Turing ecosystem, like dynamic agency. But let's look at this a bit more concretely. So I now use the advanced MH package as just an example, but you could replace it with one of the other packages in this list as well. And this package implements Metropolis Hastings algorithm. I won't go into detail, but that's a specific way to obtain such a Markov chain. And when you use this package, what you have to do is you have to define the unnormalized log density. So that means you have to define, let's go back. Here, the unnormalized log density, that means you have to define a function that computes the logarithm of the numerator in the Bayes theorem. And this is then used by the sampling algorithm to approximate the posterior distribution. And so in this specific case, you could implement it like this. You compute the logarithm of the prior distribution, and it just depends on kind of which values of alpha and beta we choose for the beta distribution, and you evaluate the log probability. And then this is kind of a special thing that you probably should do. At least I got errors otherwise. If you use a sampling algorithm that could give you probabilities, so values of p that are outside of the range of 0 and 1, then this log probability, the log prior, that will be minus infinity. But the problem is then that you can't evaluate the binomial distribution, this thing down there. It just gives an error because it's not allowed to set to use a negative probability in this distribution as a parameter. So for this simple model, we can implement the log density function in a kind of reasonably concise way, and then you can use this to define.
Hi, David. Stefan speaking here. Just a little question for understanding. This P is now not a probability, but it's just a parameter. So what was theta before? Just for matching the representations.
Yes, exactly. That's a bit unfortunate that I maybe should have used another.
No problem.
But it's the probability of hats. Yeah, exactly. Like before we had the infection rate and so on with other names, and here it's this is the parameter we're interested in.
Yeah, and P because of parameter. Got it. Thanks.
Yeah. Okay. And then this is a special thing about the advanced MH package that we don't have to go into detail. This is just how you define in the model, and really the package it's sufficient if you tell it about this log density function, and then we can use specific version of the Metropolis Hastings algorithm, and one choice here, one simple choice is this random walk proposal. So basically, in every step, you have to propose the next step, the next state, and this is what the proposal does. But if you're not familiar with the Metropolis Hastings algorithm, you can read that up, for example, on Wikipedia, and I mean there are a lot of references. But then for user now is the more interesting thing is this abstract MC interface. And as I said, it's a general interface, which the main user-facing API is this sample function. And the sample function, you just tell it the model that you use and the sampler that you use. And this is what I defined now in this example above here. And then you tell it how many samples do you want. And then it returns a bunch of samples, and here it's it's yeah, the first. Oh, it's nice. You can open this. Okay, the first value here, that's actually the parameter value, and the other one is the log probability. So the evaluation of the log density function that we implemented above. And as I said, if it's a negative value, then I mean that's not possible. So the log probability is just minus infinity, and corresponding to the probability of this value being correct is 0. And now there are some neat or nice features of the interface, because I mean, it's not only that this sample function exists, but you can, for example, discard some initial samples. So often with these methods, it takes a while. There's this so-called burn-in period until it's reasonably close to the posterior distribution, the approximation that you get. And so you can discard the first, for example, 100 samples. And you can also discard samples in between. That's called thinning. And you can change the return type. So now this is this transition structure, which is very specific to this Metropolis Hastings package. But you can return something that's easier to work with. And you get a progress bar for free as well. And so kind of with more options, what you could do is, for example, you discard the first 25 samples, you take only every 4th sample, and then you output a chains object from this MC chains package that I mentioned before. And then you get something that looks like this here, nicely summarized by Pluto here. And so this tells you which iteration it was, so which chain, if you sample multiple chains, and this tells you the parameter value, and so the value for this probability of hats that is sampled by the algorithm. And this is again the log density evaluation. And now you can sample multiple chains, also supported by this interface. And I think many people might know about the MC threads algorithm for sampling in parallel multiple chains with multiple threads, and the MC distributed algorithm, where you can use multiple processes. But a new addition to the system is the MC serial, it's called, algorithm. And before you had to write it down manually if you wanted to have multiple chains, but no parallelization, and just sample them one after another. And so this looks here very similar because we just see the first chain. But when you call it, then it's basically you also specify that you want to sample using multiple threads, and you tell the sample function that you want 3 chains. And in each chain, we want 1,000 samples. And another, I think, quite neat thing that is maybe not so well known. So these 2 points now may be even interesting for people that are more familiar with Turing ecosystem already, is that you get also an iterator for free and a transducer, but iterator is the more standard thing. And that means you can do whatever you want with the samples in between, and you just take them one after another instead of just getting the whole chain as an output of the sample function. And this is illustrated here. So the main workhorse here is this steps function. And you can read up all of this in the documentation, hopefully. I checked it's part of the documentation. But yeah, and if anything is unclear, then with all of these packages I talk about, then please open an issue, and then we can hopefully improve the documentation. And so this is just here an example of taking every sample one after another and then plotting them and creating this animation. So of course you could do much more sophisticated stuff and more useful stuff. And then, as I said, the next step usually in your pipeline is that now you got the chain. but you want to analyze it, and that's where the MC chains package comes into play. And the most simple thing you can do is to visualize the chain. And in this case, it's the free chains, since we sampled multiple chains. And here it's just the iterations versus the different values. I mean, they're all around, here, centered around 0.25. I think that was the value of P that I used in the end. And then they fluctuate, and here you can see the density estimate, kernel density estimate of the different values from all the iterations that we got. And this already gives you an impression of if there's a problem with your analysis. Because sometimes it might be that if something is wrong with your implementation or with the model or with the hyperparameters, it might be that basically all steps are rejected. So that means that you don't move, that you always have the same sample. And that's, of course, bad if you want to approximate the distribution, and it's just always the same sample that you get. Another thing that I always think is interesting to look at is this autocorrelation plot. And this,
David, can I ask a question in between?
Yeah.
Just sure. This density and the scatter plot or line plot. There, a question comes up, like, what's the reason to actually have multiple chains? Can you explain a bit? So why haven't we just merged everything together and have one big thing? What's the advantage of having, in this case, for example, 3 chains? Is there an advantage?
Yeah. So my answer relates, I would say, to actually the plot, the autocorrelation plot, and because ideally we would draw independent samples from the posterior distribution. But I mean, we want to approximate the posterior distribution, and we don't know it, so that's not something we can do. And so instead we use this approach where we move from one sample to the next. But that means that, of course, the next sample depends on the previous sample. So they're correlated and not independent anymore, as we would want to have them ideally. And so this is a motivation. So first of all, you can see this in this autocorrelation plot. You can see that for samples, where the lag distance between the different states, this relates to the iteration number. So, for example, how the next state depends on the previous state, or the state 2 steps ahead, and so on. How there's quite some correlation between them, and then of course it decreases and goes to 0 if for longer legs. So basically the sample in the 1000th iteration that is not really much correlated with the initial sample anymore. And and then I hear someone talking in the back. That's
sorry. I think it's Jan. I'm going to mute you. Sorry for being for forcing it, but no, I think it's better.
Yeah, thanks a lot. And so when you have the multiple chains, then basically that's also a way to avoid these correlations, because I mean, if you just continue with one chain, then all of the samples will be correlated in some way. But of course, as I said, after enough steps, the correlation will be very, very weak, so to say. And that's also another reason for this so-called thinning, because that when you kind of remove the samples and only take every 10th sample, then basically you already have a longer lag between them, and so they're not as correlated as if you just take every sample. And then one thing you can also do with the MC chains package is is you can look, for example, at the summary statistic. But again, there's much more things you can do with the package. And I just think that visual inspection, that's always a good first start. And then an additional thing that's often useful, I think, is to look at these so-called posterior predictive checks. So now we have a chain of samples that approximate our posterior distribution. But now we can see if we use these parameter values, these probabilities that we got here, where was it? Like here, these values 0.28, 0.3, 0.36. Then what observations would we actually expect? And is this somewhat consistent with the observation that we started with? And I mean, if there's just a huge discrepancy, then it means there's some mismatch, and it doesn't seem completely reasonable, the model or the result that we got. And I did this here. So basically, I just go through the chain and then sample from the binomial distribution with this parameter value. And then this is kind of an approximation of the distribution that you would expect. As you can see, the observed value in green and the red value indicates the mean of this distribution. They're not too far apart, kind of. Yeah, at least in this plot, we can't say or figure out that we did a terrible job. Yeah, and that's basically how you can do it for most of these individual packages, which is kind of nice. And the one algorithm where you can't do it right now is the HMC package, advanced HMC, but there's a pull request open that will hopefully fix this soon, and then it will also use this sample interface, same one. Will make it a bit easier, hopefully, for users. And yeah, and now we can move on, I think, to Turing, actually, which kind of integrates all of these different things. And yeah, more generally about probabilistic programming, the idea is that what we did right now, that's time consuming, that's error prone, especially if you have a more complicated model. So I mean, now with this simple coin flip example, there you just have this one parameter. You can write down the log density function, but it might not always be as easy. So it can be very annoying and tedious for writing, and implementing these functions. And then also, there are certain algorithms, as I said, they're better suited for specific models. So it would be nice if the computer could choose it for you, which is the best algorithm, or tell you at least when it's not fitting. And so there are reasons to kind of make this more accessible to both users and developers, because it also, the idea is that it also helps with implementing not only the models for a user, but also these inference algorithms. And so Turing is one example of such a language that allows you to write these probabilistic models. And these are called probabilistic programming languages then. But of course, it's not the one and only. So there are many different probabilistic programming languages. Like this is just random selection. There's, for example, Stan, which is kind of the how do you say, the gold standard, I would say, in many areas, especially for HMC and nuts. And then there's I'm familiar with Birch a bit because, as I said, a former colleague of mine works with Birch, and that this has some features that are not available in Turing and that you can't do in Turing. So it's also not kind of that Turing it's better than these other probabilistic programming languages. I just view it as it's different approaches, especially when it comes to, for example, comparing SOS, which is also Julia probabilistic programming language, and Turing, or Gen, another example. And so all of them have their different advantages, disadvantages, are better for specific classes of models. And I just happened to end up with kind of Turing when I got into probabilistic programming languages in Julia. And so I'm more familiar with Turing than, for example, with Saucer. The main design goals, I would say, of Turing are that the probabilistic models, they're just Julia functions, and you should be able to use basically all Julia code. So there are no restrictions, or there are no kind of whitelisted packages you're allowed to use. It's more like if there's stochastic control flow, if so the number of random variables changes, then you have to be careful, and some things are not supported. But it's not that kind of only these 5 packages are supported by Turing. And then the main way to define these models is you annotate the model function with this @model macro. And it's of course it does some things under the hood, and it might seem a bit magic, but actually it doesn't kind of change it completely what you wrote there in your model definition. The main point is really in the model you can define random variables and observations with these tilde operators. So the left-hand side, that's on the random variable. Here with the A, that's a random variable with some prior distribution. And the Y, that's an observation with some data distribution. And the reason why the Y is an observation is because it's an argument to the model. That's the main point here. So and the A was not specified before as an input to the model, so that will be sampled, so to say. And as I said, most things don't live in Turing, actually, Turing.jl, and even the model macro is not in Turing.jl. There's a separate package that defines how we rewrite the function that you provide to Turing. And then Turing.jl, the main point there of this package is then it integrates the different samplers. It integrates the model macros, the different inference algorithms. And it then also includes not only this Markov chain Monte Carlo methods, but for example, variational inference, which I haven't mentioned, and provides also tools for automatic differentiation and so on. So it integrates all the different parts of the ecosystem. And I think it's best to explain how it works by actually looking at a simple example. And so for this coin flip model, that's a possible way to implement this probabilistic model. So you can, I just called it coin flip because it seemed natural. And then, as I said, you have to use the model macro, and then you specify the number of experiments n. You specify the number of times that you got heads, and you specify these parameters of the prior distribution. And then I say now the variable parameter p that's distributed with this beta distribution as a prior, and then the observation k of how many times I see that's distributed according to a binomial distribution with then parameter p. So here I reuse the p parameter for the probability of heads. And then what you can also do so first of all, you can have keyword arguments and regular arguments. You can have a doc string, so you can document what you're actually doing, like a regular Julia function, which can be nice, especially when it's more complicated stuff and you want to write down the mathematical expressions, I guess. So in this example, it's short and not too much to explain. And then you can also return stuff. and this will be useful then in the analysis. So for example, we could return the probability and the corresponding observation that we actually used here. I mean, I could also return the then. So yeah, this is a kind of a bit special thing. This is supported in newer Julia versions, and since I run it with the Julia 1.6, I use this notation. I could also write just the kind of this way. This is equivalent. It just constructs a name tuple with parameter p and field p field k and assigns the values to this field. Yeah, I go back so that it doesn't rerun everything now. Okay, and yeah, and so the main point is now you get the coin flip function. As I said, we really try to touch this to make as few changes as possible, and this function then will create a model struct, and this model that contains the name of the model, the function how to run actually, and how to perform the sampling from the model, and then also the arguments and their default values. So we can look at this example. Now here, this was the value for n, the number of experiments, 10, and the value for how many times the heads showed up. So it was 1. And then when you run the coin flip function, when you call it, then what you get is this struct, and it stores the name of the model so that we can reuse it in different places. And this is the function where you can run the model, the f, and here it saves the arguments. So we used n equal 10, k equals 1, and these values for the parameters of the prior distribution. And then you can of course also look up the documentation just to show that it worked here. And then you, if you're curious, you can even inspect what the macro actually does. And I don't want to go into detail here, so this is a kind of I did the same model without comments again. And then what you can see here, all these parts here, they just replace the tilde with some branches and loops, and that either they sample stuff with the assume, or you observe it, so they just evaluate the log density function. And in the end, it constructs the model. So I think from time to time, it's fun to look at the internals of different packages. So and you're supposed to be able to do this in Turing as well. And then, as I said, it's just a regular function. So one fun thing that you can do is actually, I think you can overload it. So assume, for example, in this coin flip setting, that actually you don't have the n and the k, so the number of experiments and the number of heads showing up, but you just have a vector of Booleans where it indicates true and false, true if it was head and false if it was tail. And then you could define this function, and yeah, you don't have to use another name or another function. You can just extend coin flip, and now it takes a vector of flips, so the result of the experiment, and then it automatically computes the n and the k. And we can check that this actually works. So just some random values are used here, and then it again constructs the model and correctly uses n equals 6 and k equals 4 because there were 4 experiments that turned out true. Okay, and so yeah, don't be embarrassed by this and don't be intimidated, I'd rather say, by this model macro. It's really the idea is it touches only these tilde parts and doesn't change it completely what you wrote there. And then okay, let's construct the model here with the values that we used above. This is what we set above. And then when you call the model without any arguments, then it just samples, and so basically it just runs the model. And then the probability will be sampled, and then it will evaluate the log density and so on. And since we said it should return P and K as a named tuple, I can see you just get a named tuple of, and I mean, K we provided that was fixed to 12, so no surprises here. And P, that's the probability that we just got randomly now. And then we can, for example, also now with the Turing model, use a Metropolis-Hastings algorithm. And it's very similar. That's the nice thing about this abstract empty-empty interface. It looks the same, and it does not matter if you use the standalone samplers or if you use Turing. You provide the model, you provide the algorithm, and I again sampled 3 chains in parallel. Discarded 100 initial samples, took every 10th sample, just to show all the different things that you can do. And then you get this result, for example. And again, you can see the parameter that we sampled, the log density, and here the chain. And now actually here it's correct. There's in the newest release of advanced MH, it's also fixed, is that it correctly indicates the iteration. So before it still showed 1 when, even though I discarded the first 100 samples, but here it correctly shows we start with the 101st sample, and then we skipped 10 samples, and and then take the 111th sample and so on. And you can kind of recover that from the chain. We could also use another algorithm like Hamiltonian Monte Carlo, U-turn, particle Gibbs, and so on. For the sake of time, I won't rerun everything now. I will publish this notebook, and then you can play around with this if you want to try out different things, and can also change it completely. And then since it's again a chains object, that's why I thought it was also good to start with the individual samplers. The analysis is now basically the same. You end up with the same object, and you can use empty chains to plot it. And it looks similar as before. It seems to be okay. Autocorrelation plots. We can look at the summary. There is some more statistics here now because Turing saves some additional stuff. And we can do the posterior predictive check as well. And now one thing here is now that actually that's the main motivation now for why I returned K as well from the model, because I wanted to show the following feature as well. Here I again implemented it manually. So I said take the parameter from the chain, is P, and then a sample from the binomial distribution, and then we'll get this approximation of what the posterior predictive distribution look like. But I mean, I had to specify this manually, and especially if you have multiple parameters, this can be annoying. So you probably don't want to do that. And so a special feature of Turing is that actually, even if something is an argument to the model, if its value is missing, then it will be sampled. So going back to the model definition, what this means is when K here is missing, then in this line here, we will actually sample a K. And this basically allows us to sample the K now in the posterior predictive check without having to re-implement the whole model or specifying it manually. So I demonstrated this here. When you specify missing as the value for K, then when you run the model, then you get actually a random value like 49 in this case, and that corresponds to, I mean, the probability that was quite high here, so it seems reasonable that the K is also quite close to 50. And now we can use this generated quantities function to do this automatically, to use the chain and to sample the K. This function here, generated quantities, that takes the model and just reruns the model with all the different parameter configurations in the chain. So what you can see is here we had 3 chains. So we get an array of a matrix where with 3 columns corresponding to the 3 chains. We had 1,000 iterations in each chain. So we had 1,000 parameter configurations in our chain, and then we rerun the model for all of them, and then we will get different values of the p, which are the same if you. I think I removed that again. So if you compare that to the chain, you see that these values are exactly the same. I mean, that's what we want to do. We want to use the parameter values in the chain and just sample k, and then we get these corresponding k values, and and then that makes it possible to extract the values of k and the posterior predictive distribution without having to do any manual implementation of the probabilistic model, just reusing the Turing model. And I think this can be quite nice. And
a little question again.
Yeah.
Just super curious. In the last example, I spot that you used get field. This looks like you did this intentionally because x.k looks so much smaller. Is there a reason for using get field?
No, I think I used broadcasting first and then changed it to map and just kept the get field. So
I was just curious whether there's a restriction somehow enforcing this.
No, it would definitely be nicer to use just .k.
I don't know, maybe some overloading, but it's good to know that it's not an issue. Thanks.
No, not sure if it works now. Maybe I shouldn't have changed it. Whatever. Okay, and now in all the examples I use Metropolis Hastings algorithm, but actually there are algorithms like Hamiltonian Monte Carlo and this no U-turn sampler that require to compute the gradient of the log density function. And for such algorithms, that's it can be even more convenient to use to specify the probabilistic model as a function and to let the computer do the derivations. I mean, this works with the standalone packages, but also with Turing, and that basically uses automatic differentiation, it's called. So there are 2 main different modes, it's called. There's forward mode, where basically it's like every computation you do, you also compute the derivatives on the side. And that's why you work with so-called dual numbers. So the first part, that's the regular computations, and the second part, that's the derivatives. And then all the other examples that are listed here, these are reverse mode automatic differentiation. So that you kind of go backwards, kind of in a you want to think about it in a very high level, non-detailed way. And the Turing natively supports forward diff and tracker. You don't have to load anything, but if you want to use reverse diff or zygote, you have to load these packages explicitly. One special thing about reverse diff is that optionally you can also compile. It's called the tape only once. But that leads to performance improvements, but it's not available for all models. So there are some restrictions. I won't go into detail there now. The basic way how you can switch backends is with this set AD backend function, which is kind of a global switch. Forward diff is the default. And especially for the Pluto notebooks, I think it's nice to have not to deal with any global states. So you can also set this explicitly for a sampler, like shown in this example. Here, I use forward diff. And you could also use, for example, tracker here. And as a very general rule of thumb, if your model has only very few parameters, then probably you should use the forward differentiation. If the model has many parameters, many linear algebra operations, then reverse mode might be faster. And there are some restrictions also with some of the backends, like Zygote and Tracker. They don't really like loops, and it's better to vectorize computations. And yeah, there's a whole section in the documentation about this. But I think the main point is just if it's very slow, these methods, then I probably try one of the reverse mode backends and see if it helps, especially if it's available. If you can use it for your model, and reversed it, it's usually quite fast. Okay, and then I thought at the end it would be nice to come back to basically the SIR model and to show something that's a bit more fancy than just the simple coin flip example. And so we had this model here. Oh, okay. And now I just chose this parameter value. I should add, this is taken from a really nice repository by Simon Frost with a lot of different implementations of SIR models, which is modified it slightly. And these are the true parameter values, let's assume. And then we get this behavior. And now we can make it a bit more difficult, or a bit more realistic also. Let's assume that we just observe the number of cases for 40 days. And we also don't observe the number of cases directly, but there's some noise. And this is modeled by a Poisson distribution. So on average, we should get the value from the model here. But of course, it will fluctuate. And that's what you can see here. So this is what the SIR model predicted in red. And so the dots indicate the value on each day. And then the blue ones that are the actually observed values. Like, there's a missing, not everything is reported. So maybe you haven't figured out that someone is actually infected and so on. So, yeah. And then we can implement this as a Turing model. And that's what I did here. And there's some new things here I want to mention. So the first thing what we did, as I said before, we want to infer the initial proportion or the initial number of infected individuals. We want to infer the infection rate, beta, and we want to infer the recovery rate, gamma. And for all of them, I used a uniform prior. That's just because I really don't have much information about these parameters a priori, I assume. And then in these lines, I actually simulate the SIR model. And we saw before that this is just a differential equation model. And I use a standard algorithm to save that, and I also only return the number of infected, the number of susceptible individuals at every day for the days that I specify here. And then when you work with the differential equation model, one useful thing is to check if actually the simulation was successful, because it might be that you have a very weird parameter configuration, that your problem is very stiff, the differential equation problem. And then it might not be possible to actually simulate it, or at least not with the default tolerances or the default algorithm that you chose. And then you don't want to do the rest of the calculations. You just want to discard these samples, these parameter values. And that's what you can do here in this line. So this is kind of something from differential equations package. You can access the return code and check if the simulation was successful. And then Turing lets you just add a value to the log probabilities that are calculated internally. And it's not exported. And it's kind of, the reason is that you can break stuff, of course. And usually you just want to write down the tilde statements, and that should be fine. But in this special case where I want to kind of exit the function early on, this is useful. And in the other case, we compute the number of new cases according to the SIR model. This is just a way to do that. And then, I for every day, I assume it's Poisson distributed with this parameter, as I said. And again, for the posterior predictive checks, I return all the parameters and my observations to the by. And now one special thing here, maybe you've noticed that it's actually this t here, this type t equals float 64. And the reason for that is that by default, as I wrote it, it will use forward diff to compute the derivatives when we use, for example, nuts or HMCs or something that's gradient based. And when the Julia tries to differentiate through the ODE solver, then it requires that the state here is of the correct type, so that it can actually write dual numbers to that state. And this I can achieve with this type t, because what Turing does is, depending on the sampler, it will update the type. So when you use such a gradient-based algorithm, it will automatically, and you use forward diff, it will automatically change the type to one of these dual numbers. And so then the array here will be of the correct type. That's kind of special. Otherwise, I mean, I could use abstract types here, so I could use just real, but this will impact type inference, and then will usually be a lot slower. Okay, and then the next step is quite straightforward. So yeah, the times here, they are actually, I specify times as a range of integers, and this works because the differential equation package automatically promotes the elements of this tuple here. And so here I use float 64. So in the end, time will be float 64 in the differential equation package. And why the observations, they will be float 64, I'm pretty sure. Okay, so what, and then to kind of get the Markov chain, it's a very similar as before. Here I said times, I want to solve the ODE at time step 0 to 40, and 0 is included because I want to get the number of new cases. So I have to know kind of what's the difference from the first day to from the initial day to the first day, and that's why I have to include the initial time point at time 0 also in this simulation. And then the data, that's just what we simulated before. Then I use now this gradient-based sampler. I again sample just 3 chains in parallel, so why not? And discard the initial samples and thin the samples a bit as well. And then so now we can compare this to our true values. And here we had that was 10. So the proportion of initial number of infected was let me see, 10 out of 1,000, so 1%. And then we had 0.5 and 0.25, and here, this is close to centered, not centered, I should say, but peak is around 0.01. That seems reasonable for all 3 chains. And here it's close to 0.5, which was what we started with. And here it's somewhat close to 0.25. So it seems to correspond to the choices, the assumptions that we made initially. And and then the nice thing here again is that because I returned observations, I can again perform these posterior predictive checks without having to re-implement this and to re-implement the ODE solver. What you do. And now one special thing here which confuses some users from time to time is that here I specify a vector of missing. And the reason is that Turing just looks at what's the left-hand side of the tilde operator every time it encounters such a tilde operator. And so now the left-hand side of the tilde operator, that's not y, but that's the ith element of y. So if we want to sample, then we have to make sure that the ith element of y is actually missing. And also for didactic purposes, I guess it would be better to have a fill missing here, but it doesn't matter. And then we could also get rid of this get field here again. And I just plotted 300 of these sampled observations, because otherwise it's just too much. And it seems to fluctuate around the true observation. So it seems to be somewhat consistent with what we started with. This was basically the two examples that I wanted to show. Now, I mean, it's still the SIR model. It was more fancy, but still kind of a toy thing. I just wanted to show that you can also do serious stuff with Turing, actually. So people use it. And last year, for example, the Turing team and mostly Tor did this replication study of a model from Imperial College, if I remember correctly. And their model, they had used Stan, another probabilistic programming language, and we redid it and got similar results with Turing. And also, if you're interested, there's a blog post about this model, and there's also a GitHub repository with the code and instructions of how to run it. And of course, so you can run it. There are some instructions, and I think there is still some possible improvements. Of course, we also for the model, I think we added multi-threaded sampling and other features. And interested to kind of show a bit more some more complicated model here. And then at the end of my talk, I want to say, first of all, I mean, this it's not possible without all the contributors and all the other people in the Turing team, especially, I mean, Hong, Kai, Tor, Mohammed, and all the other people that I don't name now. And there's some official documentation. It also includes more information and more instructions for example, the differential equation models. And there are some tutorials, but it's difficult at times to keep the documentation updated. So if you look at the documentation and something is broken, then please open an issue, or even better if you know a fix. But that would need some love and some improvements, I think. Then there's Turing versions also of this well-known book, Statistical Rethinking. Then this really great workshop and tutorial by Jose about Bayesian inference and Turing with Julia. And last but not least, I also found this webpage by Håkan. You can also find the different Turing models. And if there's anything broken, especially in the official documentation and tutorials, then don't hesitate to complain and to open an issue. Okay, thanks a lot. Are there any questions?
Thank you very much, David. So I definitely want to say big thank you for preparing all this. It was really nice and also nice to see Amazing presentation using Pluto here. We have time for questions, sure. So please, we had a couple of questions already in the chat, but speak up.
If anybody is not going, so I have a couple of questions. Thank you so much for the presentation. I have two questions. One is, I think, for everybody, how to get involved and what kind of contributions are mostly wanted now in the Turing ecosystem. And the second question is just a quick example of something crazy that you saw that people have done with Turing. I mean, something that you were kind of amazed when you saw it. Just curiosity.
Yeah. So regarding contributions, I mean, there's of course always bugs to fix and stuff to do. We also have some GSOC students right now, but I think what would be really helpful for the community is if the documentations and tutorials would be more up to date. But of course, that's time consuming and maybe not so rewarding. So yeah, I mean, we're also doing all kinds of things in the ecosystem in Turing and so on. But still, there is this situation for when the documentation kind of it doesn't keep up with all the recent changes. Now we moved it to away from Jupyter notebooks. Now it's written in Julia Markdown, and yeah, the idea is that also that the whole setup is more similar to the SciML setup for benchmarks and tutorials. That hopefully will help us in the long run and make it easier to also change stuff and run it automated in the cloud and rerun tutorials and so on. But otherwise, there is I mean, I know about all these different kinds of refactorings going on and different features that we want to get in, but I think really the easiest way to get started is if you use Turing in your work and you notice anything that's not really working, or you read up on something, or documentation is missing, or yeah, just something is broken. I mean, when I prepared to talk, I don't know, I noticed 5 different bugs, and so that yeah. Then I prepared some pull requests and fixed some stuff, and I guess that's probably the easiest way to get started, and there you're most motivated to do something. And depending on the package, of course, there might be a list of open issues, and some that might need help, and then some that might be easier. Maybe we should add more of these labels, like to indicate that it's kind of beginner friendly and you don't have to know every small detail about the package, but could still help with that issue. And it's something really crazy. And I think the most complicated model that I saw was actually this COVID model and this COVID repo, personally, because I think I mentioned in the beginning, actually, in my own research, I don't actually use Turing. So yeah, I always think that these differential equation models, so when you combine Turing with differential equation, that's really cool, but I might be biased here a bit, and especially then when you use stochastic differential equations. I played around with that a bit, and yeah, there's I think these are quite cool. Any other questions?
So if no one else, I would have another question, and this is for getting an overview. So I expect also others who join might be the first time hearing about Turing. So just to summarize myself, so we had the samplers, where there are a couple of, and which are then integrated together with the syntax, and yeah, so this model macro, and so that you can define more easily using this tilde operator. Is there another part of the Turing ecosystem which complements this? I remember the plots. So it would be nice if you kind of sketch one time again the landscape of Turing.
Yeah. So there are these independent sampling algorithms. So when you want to implement the model by hand, you should be able to do that, and you should be able to do that without using the model macro. And then and these live in the different packages like advanced MH for the Metropolis Hastings algorithm, the elliptic slice sampling for the elliptic slice sampling algorithm, and advanced HMC for HMC. And the common point there is that they will all use the abstract MC-MC interface. So kind of the syntax and the user-facing API is very, very similar. And then if you use these packages and the chains, then you can analyze the chains and plot them and visualize them with MC-MC chains. So that's the main point of that package. And then there's also a separate part that I didn't talk about, like variational inference, just advanced VI. There's bichectors that is used under the hood a lot for defining these bijections, like when you have a parameter that's constrained to be positive. But for example, in HMC, you want to work in the real unconstrained space. And then bicheckers defines these mappings. But also you can use bicheckers for standalone things without Turing. And so the main point then of Turing is really to integrate these different samplers with the model macro, and to allow you to write down the model and then to use elliptical slice sampling, to use Metropolis Hastings algorithm, and without deriving all the distributions, implementing these lock PDF functions manually and so on. And this can be a lot easier so to write down the probabilistic models. But I think then a main advantage is also that it's much easier to change things than in the model. Like when I wanted to resample the K or in the differential equation model the observed cases, then you can't just provide this vector of missings and then automatically this stuff will be resampled. If you implement it manually, then you have to kind of rewrite the model and replace the part where you just evaluated things and computed the log density with something where you sample now. And also, for example, there's some PRs, open PRs still need some work, but where we would then take the model, write it, and derive kind of symbolic expressions for these functions, which you can then possibly massage and simplify, and that could help. So kind of by specifying it with the tilde operator, the user specifies a structure of the model which is otherwise just hidden in the log PDF and rand statements. So it's kind of more easy to modify as well for us. And
thanks a lot.
Yeah. Any other questions?
Mostly out of curiosity, do you know what the current state of GPU support in Turing is? Because last time I looked, I think there were some issues.
Yes, there are still issues, but it's it's partly in the Turing side, because when we go through the model and execute it, then we kind of collect all the different samples in some joint data structure, and that one is not very GPU friendly. But there's also a simpler alternative, which also is faster in simple non-GPU cases coming up, and this might help with GPU support as well, I assume. But the main problem outside of Turing is that also, I mean, Turing relies a lot on the distributions package for all this distribution, and yeah, other packages like stats funds for certain evaluations, and these are also not completely GPU friendly. And actually, there's a longer discussion in the repo for this COVID model, where Tor tried to summarize what the current issues are regarding GPUs, and how one could solve them. I think some problem also with CUDA was solved, or something was improved in one of the latest releases, but it's still not plug and play currently, unfortunately. But that's something that Turing developers are interested as well. But also some of the problems are kind of outside of Turing.
Thanks for the answer. Makes sense. I will have a look. I will have a look at the repo. That looks interesting.
Yeah. Okay.
One further question from my side, or some. I see, Seth, you also wanted to ask something. No. Okay. About the automatic, or whether there's some automation to actually choose between the samplers and maybe also the bijections you mentioned. So all the stuff which an end user would have to choose manually, whether there's some extra help to do this automatically.
Yeah, so actually for the bijection, that's completely hidden away from the user. So that happens automatically. The bijector defines then like when you have exponential distribution, which we know the support is positive real numbers, and then it will use the correct bijection automatically. And if you use your own custom distribution, which you can do with Turing as well. I mean, you can extend distributions and write some possibly weird distribution on your own. Then you can define which bijector to use, which mapping to use. But usually that's not something a user has to care about. But something that the user has to set is actually the sampler. And I mean, I don't remember any discussion with one of the Turing developers, Turing team about this, but I think kind of my vision would be, of course, it would be very nice to have something similar to what exists in the SciML ecosystem, where, of course, you have all the algorithms for solving the ordinary differential equation, the delay differential equation, and so on. But if you don't provide an algorithm, then it will make a sophisticated guess based on the number of parameters that you use, because the number of the tolerances that you chose. So if they're very small or rather large, and to make it as efficient and as stable as possible. And currently that's not possible because we don't analyze the user-provided model in detail, so to say. But for example, for the elliptical slice sampling algorithm, if you want to use that with a distribution that is non-Gaussian, the prior distribution that is non-Gaussian, then you will get an error message. But basically, there is no way or heuristic in place that will automatically use this algorithm if you have such a prior distribution. Which would be nice, but I also imagine it would be very difficult because there's so much freedom and I would assume maybe there's more structure in the differential equations actually that you can exploit to make educated guesses. I don't know.
Yeah, thank you for the overview. It's good to know. If there are no further questions, I think one important last point is whether you can share. You already told the presentation, so
Yes.
we can also share it via the Meetup platform, just as a comment to this event. But yeah, so would be nice to just have a link then somewhere.
Yeah, so my plan is to upload it to a GitHub repo, but I was quite busy the last days with also fixing my JuliaCon talks. So yeah, I did some stuff a bit last minute, and that's why I didn't upload it. Also, it uses the new and unreleased feature of Pluto that you can define the kind of the project and packages in line. And yeah, I would have liked to kind of to use the stable version, supposed to be released some days ago, but some delay. But nevertheless, I'll upload it probably this evening due to some repo, and then I can post the link to the repo as a comment in the meetup, and then.
Thanks so much. Then everyone should be notified automatically. Yeah, great.
Yeah.
Okay, great. Then I think there are no further questions. So I would like to thank you again, David, for preparing today's presentation and giving us the insights and overview to the Turing ecosystem and how to use Turing. It was really nice, and I enjoyed it very, very much. It was super appealing visually. I'm checking out Pluto as well. And yeah, so thank you. Big thank you.
Yeah, thanks for having me. It was really nice to get this invite from especially the Munich user group.
Yeah, nice. Also, for all who are there, big thank you for joining.